Good afternoon. Today my performance depends on my voice because I lost my voice 2 days ago. I try to make the story very short and try not to move around, stick to this platform. And I think I have many slides. Please forgive me if I skip some of the slides. The topic of my presentations is on ultra high strength materials. We have carried out research on this topic. It's funded by the Agency for Science and Technology Research together with the Building Construction Authority. Now the definition of high strengths are given in this table. We are focusing only on the conventional civil engineering materials. First is the concrete materials. The normal strength will define any concrete strength below grade 60. And the high strength is something between 60 and 120. The current technologies allow us to produce concrete which is suitable for constructions up to the strength of 180 megapascal. I mean suitable for construction in the sense that they are workable during constructions. They are able to pump to the greater height as required for most of the tall building constructions. So workability is a very, very important aspect for constructions. And this type of concrete is a low water cement ratio, very high strength in terms of their matrix, and of course aggregates are special aggregates, able to achieve very high crushing strength. And in laboratory, of course, we can do even higher concrete. We can up to 300 megapascal, but they're not so workable and not suitable for constructions. For steel, you can see in the industries, we have normal strength steel. Now very common, we have 350 megapascal steel. And of course, a special order you can get for up to 460. And the high strength steel is something between the range of 460 to 700 megapascal. And very rarely that we use the ultra high strength steel, which is beyond 1,000 megapascal for construction, except you can see from cables or some of tension members in which you do not want to do welding onto the high strength, ultra high strength steel. So a connection technology, especially a welding technology, has a very important aspect on how to use this type of high strength steel materials. Now for concretes, you can see many of high-rise building, Petronas towers with a height of 452 meters. They're using the grade 80 concretes. This is in Malaysia. And the column size is already 2.4 meter diameter when they come to the foundations. In Singapore, we have a residential buildings, the sill, 70 story, not very high. And yet you look at the column size, about 2 meters. And it's a grade 80 concrete. So this is a high strength concrete. And back to Hong Kong, you can see that 118 stories is a grade 90 concrete. So they are because using high strength concrete for high-rise building constructions. Now how about high strength steel? Look at this WFC in Shanghai here. They're using the grade 450 steel. You can see the steel material is quite thick. Okay, the plate thickness is up to 100 mm thick. And in Tokyo, Sky Trees, I was told that some parts are constructed using the high strength steel, which is a grade 700 steel. Now, if you go beyond 100, then we can see that they are applied to those cranes, which require a very high strength, and the car manufacturing up to 1,000 megapascal, you can use that. But seldom used in construction. One of the very important projects that we have realized, and this project has been completed in 2010. Now you look at the materials, and there's a called breakthrough in the usage of a high-strength civil engineering material in the building construction. It is the techno stations at Tokyo. The concrete field tube have been used, in which the steel is 780 megapascal. The concrete is 160 megapascal. So this is the first time we see the kind of high-strength material being used in the building construction. Now they have claimed that they can manage to reduce the column size from 800 mm diameter to only 500 mm diameter. They will release a usable space for the owner of the building to use. Of course, in other aspects, they're also using the fiber reinforced mortar up to the strength of 170 megapascal to construct some of the link bridge. Now in the laboratories or in the market, we can find that some suppliers that can provide this type of ultra high strength concrete materials. Look at the density of the concrete, it's slightly higher. It's about 2,800 kilogram per meter cube. So they are very compact has less bubbles or less void into it, they can achieve a compression strength 180 megapascal, quite a high tensile strength compared to the normal strength concrete. They are very low creep factors, and they are quite resistant to a fatigue. The rest are relatively increased because of the higher strength. They also have a higher Young modulus. The problem with this style of concrete is that if you put it into making a cylinder cube and under a compression test, you can see that on the left-hand side. This is ultra high performance concrete. Once you reach a maximum capacity, it will disappear. That means suddenly there's an explosion. You cannot get any unloading path. So can you imagine if you want to use this style of concrete in your high-rise building? Do not overload it. If you overload it, the column disappeared. All this load had to shape to the adjacent columns. So how to improve the ductility of this column? So we try. We put some fibers, only a very small amount of fiber, 0.25% steel fiber. You load it. It doesn't disappear. That means you need to provide some steel content to it to improve the ductility. So this is the first thing that we learn. Of course, to improve ductility, one thing is to do is to use a steel tube to provide confinements to the concrete. Now, this is called a composite construction, steel, concrete, composites. The advantage of doing that is that compared to the normal reinforced concrete design is that the steel contribution ratio has been raised significantly in this case. Now, in a normal reinforced concrete design, you can only up to a 6% reinforcement in terms of the volume contents. But in here, in steel concrete composite, there's no limit to it. You can raise beyond 20 up to 90, according to the Eurocode guidance. So then the higher the steel content you have, the higher the confinement you can provide to the concrete. Of course, the concrete also helps to prevent local buckling of the steel. And we need to have a compact sections. You cannot have a very thin plates. If you lose a confinement, yet the very brittle nature of the concrete will get into trouble. Of course, I'll show you in the program a series of experiment program under compression, bending, and fire-resistant tests that we have carried out. We show you that there's an improved fire resistance because of the concrete heat sink effect. When you heat the external steel tubes, at fire situation, the temperature rises very rapidly. The concrete will have to absorb the heat and therefore lower the surface steel temperatures. In terms of constructions, I told you that this style of concrete, I'll show you the previous slide that they're made of very fine aggregates. Now, one thing to, of course, the use of size is actually 4 mm compared to the normal 20 mm aggregates. This will help to reduce the interfacial stress between the matrix and the aggregates, and therefore achieve a higher strength. Now, the good thing is that this sort of fine aggregates is very easy to pump. So it's preferable we pump it under pressure and therefore remove the air bubbles during the construction. There's no need for formwork in this case. So we survey also in the literature what the work has been done on concrete fuel tubes. There's a large amount of experiment have been done on concrete fuel tubes. If I plot the experimental results normalized by the Cook predictions against the compression strength, you can see that large amount of tests have been conducted over this region, which is the normal strength concrete region. In the high strength regions, about 19%, up to 120 megapascal. Beyond that, very limited tests have been done. In fact, it's about 1.2% only tests, very scattered. Even up to a 250 megapascal concrete, you can see. So we tend to fill the gap somewhere in between here and provide more test experiments so that we can use this type of called engineering breakthrough in concrete technologies for high-rise building constructions. If you plot the same test data against the steel strength, you can see a large amount of tests have been done for anything below 460 steel grades. Beyond that, high-strength steel, it's very limited tests, only 7.5% have been done. So again, we want to do some also on the high-strength steel side. So we done experiment, and of course, we do the finite element analysis. These are the large, close to about 100 tests we have done, and we'll gather some of the test data. Now, some of the concrete strength, we go up to 100 megapascal. In the steel strength, up to 700 megapascal, mainly in the form of plates. So we use this plate to form box sections, welded up box sections, and infill with concrete. So we carry out some small scale tests on the short column first, ranging of different column size and from circular sections to square hollow sections. Type of concrete we compare with the normal strength concrete, together with also on the ultra high strength concrete. So this is a test we perform. We measure the strain distributions in the steel. And we try to get the concrete stress-strain relationship superimposed together with the stress-strain relationship of the steel. Then we can measure the composite test, the steel concrete composite column, and we superimpose the three, try to get the idea how the steel can provide confinement effect to the concrete. Then if you do that, there's a circular tube. It's only the S355 steel. It's the hot roll sections infused with the normal strength concrete. Now for this type of concrete, you can see that this, if it's a steel tube only, you get this type of load axial shortening behavior. Very ductile, you go up, and the strain hardening you get. But if you test only the concrete cylinder and then you go up to here, then you will crush over here. But assuming that it's ductile, you superimpose these two, you should get the superimposed behavior. Right? So this is the increase due to the concrete. This is the steel. So the maximum you can get is only here. If you combine the two, add the concrete and the steel together, you get this dashed line. But when you test this composite column, you get additional strength. Right? You go beyond. That means 1 plus 1 not equal to 2. It's actually equal to greater than 2, the two materials. That's where the behavior coming in, because the concrete actually confined by the steel tube. It provides enhanced resistance. So it's very important. You want to reduce the brittleness of the concrete, or even in the extent that you want to increase the strength of the concrete. You actually confine the concrete from expanding. That's why the concrete field tube become quite a powerful way to realize the use of high-strength materials in the high-rise building constructions. Now, once you infill it, the same tube with the ultra-high-strength concrete now, you do that. And this is the concrete that you get if you improve it. Sorry, this is the dashed line you should get. This is the concrete strength, increase over steel strength. But you test the composite tube, you get peak over here. That surpass the combine of two. But for a short while only, you start to unload. Okay, it's called sharp unloading on these composite columns over here. That causes you some alarm, but gradually, because you see when you load it, there's a separation between the steel and concrete, because steel has a larger Poisson ratio than concrete. So steel has to expand, and concrete therefore create a gap in between the two. So actually they are loading a different material, individual material. You try to sum up the behavior, you go up. Then the concrete start to give way. You lose until you crush it down and you try to expand rapidly until you get in touch with the steel again. Then there's a strength coming up. When you load it further, you see the concrete actually increase because the concrete get in touch with the steel tube. So the confinement actually getting larger when your shortening getting increased. And then you go back to the sum of the two materials, the behavior. So we compare this. These are predictions. This is called a Eurocode predictions that take into the confinement of concrete into consideration. That's enhanced in the concrete strength. And you plot the curve. You can see that the predicted result versus experimental result. Some of the double tube column actually fall outside the range. We also put double tube. It means inside this tube, we put another tube. That's because of the fire performance, and we need to have inner tubes. And some of the behavior actually fall outside that. That means the prediction by the Eurocode using this method is not conservative. And without the confinement effect, we remove it. You get the sum of the two materials. Most of the tests actually go and predict very nicely by the codes. Similarly for high strength steel, we're using a high strength steel. You can actually propose that without confinement, but that's not good enough. There are some column actually fall outside. So we conclude that for double tube column, we need to provide penalty factors into the concrete strength. We propose the use of the 15% reduction in concrete strength to shift this curve in to get the conservative predictions. And therefore, using this method will be safe for constructions. We have done a larger specimen. It's about 4.2 meter bending test. with a normal steel strength, but infilled with ultra high strength concrete, even to the box sections, using the close to S700 steel, box in box sections, and do the bending test on that. They are very ductile behavior. Most of the test results, you can see that it go up, and the steel gradually yielded, part of concrete actually crushed, and finally you get a very ductile moment rotational behavior or load deflection behavior of these sections. There's no brittle failure as observed in the compression test. We also cut up the column, remove the steel, and see that the inside, and there are some tensile crack and some compressions over here. So clearly there's a fracture, a neutral axis, a plastic neutral axis that may occur. We also carry out a long column test, 4.2 meter, 3.5 ranging from 3.5 to 4.7 meter test. Different columns, different strength of steel and concrete. And some of them are double steel tube inside. Of course, we also perform a axial force plus moment. The moment is created by changing the eccentricity of the loading from a small eccentricity to a larger eccentricity. And you get this type of, as shown at most of the column curve, you get a load deformation that looks something like that. There's nothing very peculiar about this behavior. That means this type of concrete field, ultra high strength materials, is behave as normal as the normal type of material used in the composite constructions. And of course, we investigate the material inside after failure. Now, the next series, I quickly move on into a fire test that we conducted. Now, in the fire test, first we take out the ultra high strength concrete and we heat it up without any loading. You just heat it up. Suddenly, up to 500 degrees Celsius, the concrete again disappeared. Not only under axial force, you have a very brittle behavior, but you raise the temperature, that means in fire situations, this concrete actually, without loading it, you will disappear also. So very, very violent type of behavior. Well, we say, okay, all right, then we put 1% steel fiber inside that. Try to increase, reinforce the concrete a little bit using fiber. We heat it up. About close to 500, again, it explodes. So that means the steel fiber doesn't help in provide fire resistance to this our concrete. We change to only 0.1% polypropylene fiber. So, or this is called plastic fiber. And when you heat up to 200 degrees Celsius, this fiber actually melt, provide a channel for the vapor to escape, therefore prevent any spalling. You heat up to 800 degrees Celsius, there's no spalling. So that gives us some hints that to improve the fire performance, you need to provide some degree of polypropylene fiber. Actually, we changed the content of this fiber from 1.1% to 1%. And we find that only a minimum amount will help to satisfy the fire requirements without affecting the workability of the concrete. For high strength steel, we are also not very sure about fire performance. We're also doing a tensile test. And this is just a quick summary on the fire performance of this steel. And compared to the Eurocode predictions, this high strength steel, S700 steel, do have a higher reduction factor. Reduction factor in strength reduction factor versus the temperature. The higher the strength, the more the drop. Right, you can see that. But in terms of stiffness, the reduction in stiffness behave as a normal steel. Only the strength, there's some degree of drop compared to the normal strength steel. So you've got to be very careful when you use the ultra high strength steel. So we do a compression test now this is about 4.2 meter column in the fire test. We do in the furnace. The boundary condition change from pin to fix. And test this out column again. And we hope to investigate this out double tube column. Now, the reason why we want to use double tube is that because when the fire occurs, this steel tube will be sacrificed, and we left the inner infill concrete to resist the loading during fire situations. Okay, I got 5 minutes. Thanks. So we have 22 large column test under the ISO 834 column. Failure modes expected is a buckling, but there do some very strange phenomenon occur. It's double tubes. And this is the fixed end and the pin end type. Now this one is a very, very strange behavior. This one we investigate is because of the well failure of the high tensile steel tube. These are 4 plates welded by the welding. So the welding quality here is very important. And nobody have done any tests actually on the weld. We got high strength weld. What is the performance of this high strength weld under high temperature situations? In some locations, your quality is not so good. It tends to open up and then lead to a localized failure. It's not a buckling failure. It's a localized failure. So this is just a very comparison with the circular columns, and this is the steel tube. We provide vermiculite, and this is the infill tube, infill with ultra strength concrete. Also provide some fire protections, same fire protections. It tends to plot the temperature versus the time. This is a steel tube alone. The temperature on the surface of the steel tube is very high without concrete. And that can be reduced significantly because of the presence of concrete. So the best concrete acts as a heat sink effect. You're trying to absorb the heat and remove the heat from the steel tube. Lead to a lower in the steel temperature. Again, this is the vertical displacement versus the time. This is a steel tube. Suddenly it collapses. Yet with the composite tube, it goes until there's a collapse. The fire resistance is more than 2 hours, close to 3 hours. If a steel tube alone, even with a vermiculite, 8.1%, only 1 hour. You can stretch to 3 hours. The same amount of fire protection, but with a concrete fill tube. All right, because of time, I'll skip some of them. They talk about design recommendations, and there are good recommended code of practice for designing composite columns in America. Here I see 360. In the Europe, we have a Euro Code 4. They can do the predictions. Static design, this is a fire-resistant design. In China, we also have the building codes for that. Actually, we have studied these 3 codes and try to do the comparisons between the test result. They are now, we have collected on top of that from a literature, largely on lower strength materials, plus the 71 tests that we have done, we superimposed into it. This is a ratio of the test result divided by the predicted result, analyzing by the 3 code of practice. I just illustrate using a Euro Code 4. You get all this, you plot against the cylinder strength. So you have a more test result coming up over here. You plot the design value, that means the test result divided by the design value. This curve all shift up because this is based on the characteristic value. This is the design value. You can see there's no reason that you cannot extend the current code of practice to cover even the ultra high strength concrete. Of course, with the recommendation, we recommend that for double steel tube, you need to move this data up by using a factor of safety of 0.85. So for this 3 method, the average ratio for the 3 code is above 1.0. And the concrete limit should be safely extended to the ultra high strength regions, I mean up to grade 180. But we know that there's absent in test data, somewhere in the region between concrete strength of 120 to 140. There's not much test over this region. That's why the research now, I'm going to complete very soon, end of this year. We're going to extend it to Australia in collaboration with Professor Brian Liew. We decided to carry out another 3 years investigation on concrete fill column, but focusing on the concrete strength between 100 and 120 megapascal to fill the gaps. Okay, the Euro code or the other 3 codes predicts the test result well with a design ratio. This is a design average against the test average ratio of 1.33. Only 3% of test data actually less than 1.0 out of the close to 200 test data that we have. Conclusion also that spalling of the ultra high strength concrete can be avoided using by additional of 0.1% of the PP fibers. Now, just the last 2 slides, why we want to do it. Also, you look at, we have done some comparison between using the conventional reinforced concrete column design with the rebar here, up to 6% you can put in. That's one kind of design for high-rise building. You can infuse steel tube. Most common steel now is X355 with a normal strength concrete. And then, of course, if you do that, there's some saving in terms of the column size. Probably about 10 to 20% size saving you can have. And if you opt for ultra-high strength concrete, infill this steel tube with ultra-high strength material, again, you get about 10% reduction in size. But ultimately, if you go to ultra-high strength concrete with a high tensile steel, the column size from here to here is about close to 50% reductions. We studied a 50-story typical buildings. We found that about 50% reductions in the column size that we have. But most important, we are going to a thinner steel tube. For constructions, it's much productive if you get thinner plate with a high strength. But whether you can weld it properly, the weldability of material, you handle it very carefully. You can see a number of welding of 40 mm thick materials. Compare that, you're welding a much thinner steel tube. The number of welding operations actually reduced quite significantly. They lead to a significant saving in the construction time. With this, thank you very much for your presentations.